Great. Thank you very much for this opportunity to present here today. So I'm just going to give a brief overview of field monitoring technology and how you can get started yourselves and implement field monitoring technology in your own workflows, detailing some of the acquisition and reconstruction frameworks, and then follow into our experiences and applications on the Connectome 2 scanner and beyond, and try to finish off with some of the challenges and ongoing work that we're trying to address in this regard. So I think it's fair to say that across all MR modalities, image imperfections or image artifacts plague a lot of our applications. And one of the dominant sources of errors comes from eddy currents, as shown here. And you can imagine that as we're scaling to higher performance systems, so higher gradient amplitudes and slew rates, this is going to exacerbate these artifacts. So one way to combat these imperfections is to utilize something such as field monitoring. This is an ensemble of 16 NMR active field probes commercially produced by Scope, as shown here, which can measure the dynamic field evolution during our scans. And then we can take this information and inject this into our reconstruction pipelines to mitigate artifacts, as shown here. So what's going on behind the scenes is we have these probes distributed throughout our imaging volume, and we use some sort of basis, so typically a spherical harmonic basis set to characterize the field fluctuations utilizing few field probes. So with 16 field probes, we can measure up to third spatial order in space. And here I detail the different types of field perturbations that we can measure. So 0th order is this global field offset, and then you can see first order corresponds to our linear gradients and so on and so forth for higher order, more complex field perturbations. And this on the left side is detailing over the course of a scan acquisition, the various field fluctuations that we can measure. And this is coming from a probe system. So we extract our probe's signal. Because it's complex signal, we can look at the phase time courses and then fit this spherical harmonic expansion to it. And then we can also leverage the fact that we can inject our off-resonance, static off-resonance field maps and sensitivity coil profiles into a signal model. So we refer to this as an expanded signal model. We can also then take our raw data from our scanner and implement this in some sort of iterative conjugate gradient sense-based reconstruction offline. So these are some of the setups from Scope. Here I'm highlighting the first generation acquisition system and how this communicates with the scanner and a field camera. And then this is the latest new Neox acquisition system. And we have this on our 3T and 7 Tesla bays. And for more information on this, Cameron Cushing will be here during lunch for the demo. And so how you can implement field monitoring in your own sequences, you can take TTL trigger pulses and put these ahead of anything you want to spatially encode. So here we're putting an EXT trigger ahead of this EPI readout so that we can measure the field fluctuations going on during a readout. And on the Connectome 2 system, we have offshoots of these product sequences. So our pulse sequence programmer, Danny Park, has made modifications to EP2D diff and EP3D diff for capabilities of field monitoring for 2D and 3D diffusion EPI, as well as we utilize in-house PulseX sequences such as multi-shot EPI and spiral diffusion. And then Scope on their GitHub has a plethora of sequences you can also access at your own leisure. So once you have your Scope data, if you're interested in reconstructing images, you can utilize Scope's platform. So this is Scope DM and Scope I, where they do the data merging offline. And then you have your data in an MRD stream, which you can then forward over to some sort of advanced image reconstruction platform. There's also open source platforms available. So one that we use is based in MATLAB, and we intend on making this all publicly available. So our scripts, our demo data, and some of our PulseX sequences. And then this is the reconstruction toolbox that's open source. So to look at some of the results now, taking you back to some of the early field monitoring measurements on the Connectome 1 scanner. This is coming from Gabriel Ramos-Jourdain, which motivates the use of field monitoring for high resolution 3D EPI. So they were suffering from these pretty substantial ghosts, and irrespective of doing something like a phase correction or a mu style approach, as you can see with field monitoring, this substantially mitigated these ghosts. And now what we have on our Connectome 2 scanners, so we have the ability to do sequential field monitoring. This is utilizing a dynamic field camera. So what's going on actually is if we are to look at our trajectories, typically what we do is we input our nominal trajectories into some image reconstruction pipeline. And you can see as we zoom in on the periphery of this spiral trajectory here, the nominal trajectory that gets pushed further and further out if we use the measured trajectory from scope. And then if we also include a B value of 1000 in our, so the diffusion gradients, and this is coming from the strong eddy currents. And then extending this with higher and higher B values, you can see for this EPI as the trajectory is shifting from left to right with these B values upwards of 10,000. We also want to extend our applications to non-Cartesian trajectories. So what field monitoring can do for us for something like spiral is for spirals are very sensitive to these field perturbations, especially if we have the eddy currents from diffusion. So we're trying to target these mesoscopic regimes. Here we're looking at an example of 450 micrometer spiral acquired on our Connectome 2. And on the left here, we have a B0 image utilizing just a non-uniform FFT. And then here you can see the mitigation and the blurring with utilizing the scope measurements, as well as for the diffusion images. And so we took this a step further to try and leverage our spiral acquisitions to use shorter echo times and the grading capabilities of the Connectome 2 scanner. So here we have an echo time of 19 milliseconds for spiral in comparison to EPI at a resolution of 550, showing how despite the longer readouts at this higher resolution, we're still able to preserve that the sharpness in our spiral images compared to our EPI, and noticeably the overall improvement in signal across our spiral images. And then taking a closer look at some of our fractional anisotropy measurements. So highlighting some of the white matter tracts here, so how we're better able to delineate something like the line of Gennari as outlined here with the spiral. Sticking on the topic of spiral imaging, so Zijing Dong, Fushu Wang, and company have, of course, they've explored some of the applications of EPTI, so this ability to measure different echoes for distortion-free EPI images. So Xingwang Yang and Burke and Bilgich, they've been looking at how they can apply this to something like a rotated spiral. So with a spiral, you have the ability to acquire in a single echo the center as well as the periphery of K-space. And then as you can rotate your spiral, you can get more and more echoes and then introduce various shots to get something around 50 echoes. And these are some preliminary measurements showing how the scope system is able to get more appreciable monotonic decay in comparison to just utilizing non-uniform FFT. And this is also outlined in the mask as shown here. So also capabilities to look at the gradients themselves. So not for the imaging purposes in this context, but something that Renzo Huber has been religiously exploring is these fuzzy ripples and these edge ghosts. So coming from effects such as readout imperfections. And with the scope system, we can kind of measure some of these effects on the rising edges from these short-term eddy currents. As very noticeable on the Terra X, and this can impact things like high resolution layer fMRI, which I'm sure he'll be talking about later. Taking this a step further, how we can utilize the system is to measure the ability to correct utilizing something like prospective eddy current correction coming from Hao Tianhong, Jason Stockman, Bastien Guérin, and Renzo Huber, where they're looking at localized dynamic field shimming. So you have these 31 channels, and then you can kind of map utilizing some sort of basis set and provide a magnetic field to combat the eddy currents and the GPA overshoots that are being produced. So as you can see, the scope system, we can get better to the nominal gradient here, and then hopefully we hope to see what impact this has on our images. Lastly, I just want to quickly touch on, you have to be conscientious of what probe systems you're using. So dynamic field cameras are closer to isocenter, where they're sampling the linear region of your system. But we have on loan, courtesy of Joseph Vu, this NeuroCam 3T, where these probes are further from isocenter and they're elevated overall in Y by a couple centimeters. So this can greatly also impact the fitting accuracy. So we've explored different correction approaches to try and get better results in comparison to, say, the dynamic field camera as shown here in black. So what I've kind of touched on is our workflow utilizing an offline reconstruction. It isn't without it. It is with its challenges. So we have to manually transfer our data, process it all offline before reconstruction. So this is a little time consuming, and we don't know what our images look like at face value on the scanner. So this necessitates something like automated, fast, and real-time workflow. And we're happy to be working very closely with Scope to try and get this streamlined to be able to stream our data to a computer on the server and then do reconstructions and have some sort of approximation that we can look at while we're scanning. So we're very excited to see where that goes. Thank you very much for your attention, and I'm happy to answer any questions if there's time. Yeah.